I think it's recording. So, hello everyone. My name is Dr. Suraj Jaiswal and welcome to the second tutorial of the course entitled Simulation of a Mechatronic Machine. In today's tutorial, we are going to model a crankshaft, and as you can see in the sneak peek, a crankshaft is shown where the reciprocating motion of the piston causes a rotating motion of the crankshaft. And of course, in this sneak peek, a number of cylinder pistons are shown. But in today's tutorial, we are just going to model one cylinder piston. Now, this mechanism is also called a slider crank mechanism because this piston is actually sliding onto the cylindrical chamber, right? So, it is also called as slider crank mechanism, or the principle remains the same. Now, if you have not followed my first tutorial, I will highly suggest that please follow the first tutorial of the course, then the second tutorial will be more enjoyable for you. So these are the list of content that I will be covering in today's video. First, we will briefly see what are the requirements in order to model a crankshaft. Then how we can model it using number of bodies, joints, rigid transforms, get rid of redundant constraints, and plot some results. Then finally we will see that how we can carry out the kinematic and dynamic analysis of such a system. So if I'll ask you what is a crankshaft? A crankshaft is a rotating shaft that converts the reciprocating motion of the piston into the rotational motion of the crankshaft. This kind of mechanism is most commonly used in internal combustion engines, as I already showed you in the sneak peek. Now, as I mentioned that we are going to model only a single cylinder piston, as you can see in the picture here, right? And its degree of freedom is 1. Why? It's because if you visualize if there is a reciprocating motion of the piston, then the crank will follow. And vice versa, if there's a rotation of the crankshaft, then the piston will follow. In either case, just one motion is enough in order to define the entire dynamics of the system, right? Or just one motion is defining the motion of the rest of the system. So that's why the degree of freedom is 1. Now, if I'll ask you what are the requirements in order to model a crankshaft, of course, whenever we start thinking about modeling, we always think with respect to a reference frame, which is called the inertial reference frame or the global coordinate system. And this global coordinate system needs to be on some ground, correct? And then, of course, we need gravity because gravity is everywhere. Now, if you see this picture, how many bodies are required? We can see there is a red body, green body, and blue body. So, 3 bodies. Now, there are some joints with respect to between each body and also with respect to the bodies and the ground. So, if you will see, we will need 4 joints. One joint between ground and body 1, second joint between body 1 and body 2, third joint between body 2 and body 3, and fourth joint between body 3 and the ground, which is the sliding joint. Now, you know that we are going to use Simscape Multibody in order to model this system. And in Simscape Multibody, everything is modeled in everything is modeled in 3 dimension. Now, if you have been taught this kind of a system in 2 dimension, that's fine. Because at the end of the day, it's a planar mechanism. So no matter you model it in 2 dimension or 3 dimension, it's only going to have a motion in one single plane, correct? But if you want to calculate the degree of freedom using the mathematics, you know that in order to define any body in space, in order to model any body in let's say 2 dimension, you need 3 coordinates: the x-axis, the y-axis, and the rotation in that plane. So You have three bodies, so three bodies will require 9 coordinates, and then you have four joints. Of course, we know the fourth joint is a translational joint, and we can assume that all the other three joints are revolute joint, right? Because there is some kind of rotation with respect to of body 1 with respect to ground, then of body 2 with respect to body 1, and then of body 3 with respect to body 2, right? So these three joints, we can assume, we don't know what are they, but let's assume that they are revolute joints. So each revolute joint in two dimension introduces two constraint equations. So and each translational joint in two dimension introduces also two constraint equations. So three revolute joints introduces six, and then one translational joint introduces additional two. So a total of eight constraint equations that you have in 2D and 9 coordinates. So 9 minus 8 is it's 1, correct? Now, if you try to calculate the same degree of freedom in 3 dimension, you will realize that in space, in order to define any body, you need 6 coordinates, 3 translational and 3 rotational. So three bodies will have uh, 18 coordinates. And then, since we assumed these three joints to be revolute, each revolute joint introduces 5 constraints in 3 dimension. So it will introduce 15, and this translational joint introduces additional 5 constraints in 3 dimension. So another 5, which makes it 20 constraint equations. So 18 coordinates minus 20 constraint equations, the degree of freedom is becoming to be minus 2. So here is the trick. We know it's from our logic that the degree of freedom is 1. But our mathematics in 3 dimension is saying that the degree of freedom is coming to be minus 2, which cannot be true, right? So either our logic is incorrect or our mathematics is incorrect. In this case, we know our logic is correct because there is only one motion, there is only one degree of freedom, one motion which defines the motion of the rest of the system. We know that, and we have seen it already in the sneak peek. So of course, the mathematics is somewhere wrong. I will not say the mathematics is wrong, but we assumed the joints to be revolute joints, right? And there is where we made a mistake. Of course, in the beginning, we are going to model like all these joints to be revolute joint, and of course, we know by default this is a translational joint, so we are not going to talk about that. But in 3 dimension, you realize you introducing redundant constraints. Is why? Is suppose there is this is a crank and this is a connecting rod, correct? So let's say this is body 1, this is body 2. Then you know that this particular, if there's a revolute joint here, then of course this is going to rotate like this, correct? And also if there's a revolute joint here with which it is connected to piston, it is also going to rotate like this. Now for you, it's not necessary to have a connection between these 2 points using revolute joint only. It can be replaced by any other joint so that you can take care of the mathematics, and this is what we will see in today's tutorial. Okay, now if you realize I'm not naming them as body 1, 2 and 3, but I'm using them a more sophisticated name as crank and things like that, because we are engineers and it's very important for us to know the exact nomenclature as well. So this body 1 is called crank, body 2 is called connecting rod, body 3 it's called piston. The joint between body 1 and 2 is called crank pin. The joint between body 2 and 3 it's called piston pin or rest pin. It's important for you to know this nomenclature because if you go to industry, people might name it as crank, connecting rod, and piston, and not like body 1, 2, and 3. It's just I'm explaining you to make the explanation simple. Now, let me take a screenshot of this particular system, and then I want to draw some things here. Now, I believe it's very important for anyone to first understand what they are modeling it, rather than directly jumping into the modeling process and getting lost there. If you have understood the requirements carefully, and if you have understood the different aspects of the model itself, 50% of the job is done for you. The rest 50% is just to follow the instructions and model it. So let's analyze this system. Now, if you see the crank, the body one, we know that we need a point here because this is how it is connected to the ground. So if we imagine the x-axis along the body and the y-axis perpendicular to it, so we need a reference point in the body coordinate system, which we also called as frames in the Simscape Multibody toolset, right? Then of course we need a point here in body 1 and point here on body 2. And of course there's a third coordinate as well, which is coming out of the plane. So z is out of the plane for us, right? Z is like coming out of the plane. So we need 2 points on body 1. Similarly, we need 2 points on body 2 as well. One at this location with respect to which it is connected to the first body. So one along the length, which is x for body 2, and y perpendicular to it. And then of course we need another point here, which is x along the length of body 2 and y perpendicular to it. Similarly, if you imagine body 3, then this body 3 is connected with body 2 at the same location. So we need a point here where we can say x is the way our global coordinate system is, and y is along the length of the piston. Correct? Then of course as a slider crank here, of course you can define a point here, but what we are trying to do, we are just trying to define a point at the center of the body, and then we say that the slider, the translational joint is just translating about the center of the body itself. That is just a simplification. Now, if this requirement or this uh, overview of the system, if you have understood it, you have understood 50% of the task itself. The remaining 50% is just following the process. So let's see. Let's open our Matlab. It will take a while. I am using Matlab 2023 A version, so which is slightly different from the previous versions of Matlab. But if you're using a previous version, it doesn't matter. It's just the user interface will be slightly different. But the overall principle, what I'm going to teach you in today's tutorial is going to remain the same. It will take a while, but let's see what we have in the presentation next. Okay, so we have the modeling process already. Before we you start modeling, make sure that this folder over here is the folder where you want to save your file. For me, it's already pre-selected that I want to have it in this folder structure. So if you're not sure, you can go to this browse for folder and then select your appropriate folder onto your system. I have it here already. As you can see, my presentations are in this folder. So now in the command window, I want you to write sm new. So it will open a new Simscape multibody file. The status is showing busy, so it takes a while to open the first Simulink window. Almost there. So if you recall the requirements are we need a ground, we need a inertial reference coordinate system on the ground, we need gravity, then we need three bodies and four joints. So by default, we already have some component block in this Simscape multibody file. So just go ahead and save your file the wherever you want to save it. I mean, in the same folder where I just mentioned in the Matlab folder structure. So this folder is already selected for me. Let me rename it as crankshaft underscore YouTube, and you can save it as .slx file. Always save your file because sometimes if you don't save it, your data will be lost, right? So if you have followed tutorial 1 already, you know the basic user interface of this particular software. So I'll remove some of the components that I don't need, and I comment out some of them which I don't need at the moment. So let's comment out, and I'll just remove them for simplicity. Okay, I'm removing it somewhere here so that you don't see them. Now, if these names are not coming for you, just select, go to format, and you can make the name visible for you. Okay, it will be visible. So let's figure out, we already know the requirements. So let's start with the modeling process. We need a ground, and the world frame is already taking care of the ground and the inertial reference frame. So if you double click this, you will already you see you don't need to change anything because it's already taken care of, right? So ground and the global coordinate system or the inertial reference system is already taken care of. Next, gravity. If you go to mechanism configuration, over here, you see the gravity. This is the x coordinate, y, and z. By default, Simscape Multibody assumes that the gravity is in the minus z direction. But since we are modeling our entire system such that x is horizontal, y is vertical, and z coming out of the plane. So we need the gravity to be in the minus y direction and not in the minus z direction. Correct? So we need to change the gravity from minus z to minus y. So now this is x, y, and z. You press enter and you don't need to save it, it's already auto apply, and close it. So we took care of ground, we took care of inertial coordinate system, we took care of uh, gravity. What we need to do next is we need to model the bodies. So for the first body, I'm using this brick solid. So I'll right click and I'll uncomment. Let's rename it first of all as crank. Okay. Uh, I hope it's visible. Correct. And I'm renaming it as crank because all this naming is very important for us so that we don't get confused when you are trying to model a very complex system. If you don't name it correctly, you will be lost, and we don't want to get lost, right? So double click this. The first and the foremost thing I tell you is rotate this block such that y is facing upward, so that this is how we are modeling our system to be, right? Correct. Now the dimensions are x, y, and z. For the crank, if you follow the slide, let's go back to the slide. If you follow the slide, we can get the dimensions from here. So for us, okay, I already have the dimensions in the next window, so I'll just briefly type it. So of course the dimensions are mentioned in millimeter. Always enter them in meter. So because we are following one unit throughout, which is the SI unit. So it needs to be in one consistent unit throughout. Don't get confused. So for us, length is 0.35, breadth is 50 millimeters, so 0.05, and height is 50 millimeters, so 0.05. Enter and update using F5. So this is my first crank or body one. Then go to inertia properties. We want the inertia to be calculated from geometry based on density. Density will be that of steel, which is 7,800 kilogram per meter cube. Enter, update the derived values. So all my mass, center of mass, moment of inertias are updated. Then of course, every time you make a change, you can press F5 in order to update the visualization. But of course, there will be no changes because these are internal properties of the body. Then I want this body to be red in color. So go to graphics, visual properties. This color is red, green and blue. I'll increase the red value to be 0.9. Enter and press F5 or the shortcut here. So now my body becomes red in color. Now if you go to frames and if you press this visibility of frame, you will see by default this frame R, which is at the center of the body, is already there. Now let's go back to this Matlab window. Now the moment I press this, uncheck this box R, and of course you need to update the visualization. It doesn't disappear here. The moment you press apply, you will see this disappears from this port disappears from this component block here. So the moment I apply, this disappears here, and we don't need the center R in our component block. So that's why we are removing it. But if you recall it from here, we need one reference frame here and one reference frame here on the body one, right? So let's define one reference frame. So go to new frame. Let's rename, keep the name as F1. We define the first, use the select option. We select the surface, press based on geometric feature, use selected feature. So centroid of minus X surface is where I want my first frame to be, and press save. So you see my F1 is here. Now similarly, go to new frame again, name it as F2, select the surface, press based on geometric feature, then press use selected feature. So centroid of plus X surface is my new frame, and then press save. So my two frames are ready. Don't get confused the moment you press this isometric view and the block is oriented differently, because you see Z is again up here. Always you need to reorient such that Y is upward, and then the modeling, it's just for our own sake. So we know how we are modeling the system, and press OK. So now my crank is ready, such that F1 is at the bottom, F2 is on top, and I'm just like changing the shape of the block the way it is so that it helps me in the modeling process. I always try to reshape my block so that I know how my bodies are being modeled, correct? Now, in order to model the connecting rod, I realized that the dimensions of the connecting rod are the same, only the length is changing. So what I can do as an engineer, I'll simply copy paste it. I'll select, press Control, and then drag. I'm renaming it as connecting rod, and then I go to this body. I only need to change the length, which is 1000 millimeters, so 1.00 meter here. Enter and update. You realize the length is updated, but at the same time, if you press this visibility of frame, the frames are also automatically adjusted, so you don't need to do anything. Then of course inertia remains the same, which is that of steel. In the derived value you need to update, so now the mass, center of mass and moment of inertia are updated. And I want this body to be not red in color but green in color. So I'll just increase the green value. So in this RGB, increase the green value, enter, press F5. So now the body is updated and press OK. Remember, of course, you are copy pasting it, but copy paste it with care, and that is what is important uh, for engineers like us. Now it's slightly bigger in length, so I'll just reshaping it. Now we need the third body, which is piston. So in order to model a piston, we need to search for cylindrical solid. So if you search cylindrical solid, rename it as piston, and let's go to this component block by double clicking, and I say that the radius of this body is 100 millimeters, so 0.10 meter. Length is 150 millimeter, so 0.15 meter. Then in inertia, I want it to be based on uh, calculated from geometry based on density, and that too density of steel 7800 kilogram per meter cube. Enter. Then in derived value, update the derived value. So now it's uh, the mass, center of mass, and moment of inertias are updated. Then I want this body to be blue in color, so I'll just increase the blue value, enter, then update. So now you see my body is updated. And remember what I told you in the beginning, you always need to reorient before starting anything. So the moment you reorient, you realize your piston is not like this, but like this. Now, here's the thing. Cylindrical bodies in Simscape Multibody are modeled in such a way that the length of the cylindrical body is along the z-axis. And for this reason, the length of the cylindrical body is along the z-axis. But let's not worry about it at the moment because we can take care of the rotations of the axis using rigid transform. So let's reorient this at the moment. And by default, we notice that there's a center frame R already in this body. If you go to frames, right? So we will use it because if you remember this particular picture, we need a reference frame here at the center of the body, but then we also need a reference frame at the bottom of this body of the piston. So go to piston. Let's rename it as F1. That is fine. Then select rotate using the cursor center cursor button. Select this surface based on geometric feature. Use selected feature. So now you can see how the X and the Y and the Z are here. And we can press save. But before saving, of course, we know that this entire coordinate system is something different than what we want it to be. But we will still go ahead and save it and later take care of it using rigid transform. And then press OK or save. Apply or OK or directly OK and it will do the job for you. So now we know that F1 is at the bottom, right? Or we want the F1 to be at the bottom. So select the block, press Ctrl R to rotate the block. So now this is my piston. And it's slightly like this. Okay. I'm just making space for everything here. Now let's go back to the slide. So we have modeled all our bodies and we modeled it in a similar way. So you can see the same things are here. Now let's go ahead and model are joints. Now, by default, we know that the joint 4 is a translational joint or a prismatic joint. And in the beginning, we are assuming all the other three joints are revolute joints. So that is fine. That assumption is not incorrect. So we search for a revolute joint. We name it as joint 1, such that the base frame of this joint is connected to the ground, and the follower frame is connected to crank, right? If you follow this picture, you know that this revolute joint here is oriented in such a way that the body is not horizontal but at an angle, and this angle is, let's say, 45 degree. And since it's in counterclockwise direction, so it's plus 45 degree, right? So what we can do, we can go to this revolute joint. In the state target, we can define a position target where we say that we want this body or this joint to start from at an angle of 45-degree counterclockwise and set the priority to be high. High priority means that your solver will try to fulfill this criteria completely with high priority, and low priority means it will try to fulfill all the other high criteria in the model, and at the same time it will try achieving to fulfill this low criteria as well, but we want the criteria to be high, so let's save it as high and close. Okay, so our first joint is ready. Now for the second joint, of course, I can copy paste the first joint as well, but we remember we gave some initial position target. So for that reason, I search for revolute joint again, and I am renaming it as joint 2, and then go in order to go to next line, press uh, wait. Mhm. Shift enter. Yeah, it was shift enter, and this is a crank pin, correct? So joint 2 is a crank pin. Now it also has a base frame and a follower frame. Since we are modeling from one direction and going to the other direction, so we start with modeling for world frame, then we connect the base frame of joint 1, then go to the crank, and then in order to go to connecting rod, we want this base frame to be connected with crank only. So we just press Ctrl R to rotate it so that base frame is facing the crank. Don't make connections yet, but just put them in the right positions. Okay, I'm zooming out a little bit. So two joints are taken care of. Now my third joint is also a revolute joint. So you can actually simply copy paste this one here. So select, press Ctrl and drag. This is joint 3, and this is actually piston pin, correct? And place it here. Don't make connections yet. And we have our piston here, making just space for everything. Okay, now if you realize that this piston pin or joint 3 needs to be connected with the piston. So now if you follow everything over here, they are in the coordinate system that we want to define, such that x is horizontal, y is vertical, and z is coming out of the plane. So joint 1 is also like that, because remember revolute joint rotates about the z axis. So this is fine. Crank, we also defined it in such a way. Joint 2 is also defined it in such a way. Connecting rod is also defined it exactly in the same principle. And again, this joint 3 is such that it's a revolute joint, so it's going to rotate about the z axis, correct? But The piston is such that the length of the piston is about the z-axis and not like this. So what will happen if you just simply connect the follower frame of joint 3 with the F1 frame of piston? Instead of this system, I mean, if it's connected here, so it's going to make a motion like this, right? This connecting rod. But instead of this motion, what it's gonna do, it's gonna make the piston move like this, because the rotation of this joint 3 is about the z-axis. And then the moment you connect it with F1, and F1 is at the bottom of this piston, it's also going to rotate like this. We don't want it, right? We want the piston to be like this, such that this joint is here and it's rotating about the z-axis. So what we are going to use? We are going to use a rigid transform. So let's take this rigid transform, which is already here, and we right click and uncomment. So now before connecting anything or defining this rigid transform, we need to decide which frame of the rigid transform is connected to which system. Let's say the base frame is connected to joint 3. So I'll just rotate using Control R, and the follower frame is connected to the piston. This is very important because the way it is connected with the with the respective component block is exactly the way we want to define things in this rigid transform. So if you double click this, now do we need any translation of the coordinate axis? No, we want only the rotation of the coordinate axis, correct? So under rotation, we want to use the aligned axis method. Of course, if you want to use other methods, you're more than welcome. But in the aligned axis method, if you see, two pairs needs to be defined because we are dealing in 3 dimension. So the moment, if this is one coordinate system, this is another coordinate system, the moment we say that uh, any two axes of this coordinate system needs to be aligned with two axes of this coordinate system, then the third axis will follow by default, and then it will take care of things. So if you go to this piston and if you reorient this, no, let's keep it like this, right? Of course we want our system to be like this, but is our coordinate system like this? No. How is our coordinate system? Our coordinate system is such that the x the x is horizontal, true, y is vertical for us, and z is coming out of the plane. So what we can do in this rigid transform, of course, if you see here, the base frame is connected to the rest of the system which follows the correct coordinate system, but the follower is frame of the rigid transform is connected to the wrong coordinate system, is connected to F1 of the piston, which is uh, in the wrong coordinate system. So what we are going to say is, let's make enough space for everything so you don't get confused. Uh, Actually, I need this picture. Okay, let's. Okay, so we are going to say that the follower frame z-axis. So in the follower frame z-axis, the piston length is defined in the z-axis. Whatever happens in the z-axis, we want this to be projected onto the y-axis of our base frame. Base frame is connected to the system which is correctly defined. So what I'm trying to say, this is how my piston is defined, right? The length is along the z-axis. I'm saying whatever happens along the z-axis, project it onto the y-axis. Correct? And then since x-axis remains the same, so you can say the whatever happens in the x-axis of the follower is also on the x-axis of the base frame. the moment I define these two pairs, things should be fine for this particular frame F1 of the piston. This is very important for you to understand, okay? Because things are oriented like this. So whatever happens in the z axis, actually we want it along the y axis of our coordinate system, right? So that's how we are defining this rigid transform to be. But if something is not clear for you on rigid transform, I have already made a video on my channel about rigid transform. I will highly suggest you to watch that channel, that video on my channel. So my first rigid transform block is ready. You can simply close it. Before closing it, I want to show you something. If you go to frames and go to this frame F1, so either you can define a rigid transform using the external rigid transform component block, or when you are defining these frames, you can already define these axes. You see primary axis and secondary axis. You can already rearrange these axes the way you want it to be. So even this can be a simple approach, or this can be a simple approach, but I prefer, I will suggest you to model it as a rigid transform so that you know which coordinates are being transformed by just looking at the simulation file. Because if you define things internally, you will get confused, like what is defined in which way and what not. So that's why. So just save this, and this component block is ready to be used. Now, of course, we need the fourth joint, which is a primitive joint, which is also prismatic joint. I mean, sorry, not primitive joint. I have been saying primitive joint, but it's a prismatic joint, which is also called translational joint. Okay, so let's rename this rigid transform as rigid transform 1, and this prismatic joint as joint 4. Shift enter. This is a prismatic joint. Okay. Now, the way revolute joint rotates only about z-axis in Simscape Multibody, similarly, the prismatic joint also translates only about the z-axis. So if you go to this prismatic joint, you will see that this prismatic joint allows translation about only the z-axis, which is good for us in a way that the length of the piston is about the z-axis, right? So if you see this r is translating about the z-axis, which is along the length of the piston. If this is the length of the piston, it is translating about the z-axis, and we want the point r to translate, and since we want to connect it to the prismatic joint, which also translates about the z-axis, so we say, okay, this r on this particular piston, let it translate about the z-axis, and that's fine. So we can simply make a connection between them. But do we want this translation about the z-axis or about the y-axis? About the y-axis, right? So what we can say, we can introduce another rigid transform at this end of the prismatic joint. So we say it's fine. The length of the piston is defined about the z-axis, and we also want to translate about the length of the piston. So this frame R of the piston and frame F of the prismatic joint is fine. So they both are consistent with each other, that hey, the translation should be like this, correct? Along the length of the piston. Fine. But we can say that whatever translation you see in this particular axis, we want them to be on this axis. So what we can do, exactly the rigid transform we defined right now, we can just copy paste it using control then drag and rotate it such that my follower frame is connected to the wrong coordinate system still, and the base frame is connected to the right coordinate system. You remember the similar way we defined here that base frame was connected to the right coordinate system and follower frame of the rigid transform was connected to the wrong coordinate system point. Similarly, we just reorient this. We copy pasted this rigid transform, rename it, and rotate it in, or connect it in such a way that the follower frame is still connected to the wrong coordinate system point and the base frame is connected to the right coordinate system point. Okay, so let's see. Uh, Go back to the slides and let's see if I've covered everything. So yes, I have covered this. Uh, then we have covered exactly this as well. And now we can simply go ahead and connect our system. Okay. So let's connect our system. So the world frame is connected to the base frame of joint 1. So simply select the port and then drag, which will be fine. Then my follower frame of joint 1 is connected to F1 of crank. Then F2 of crank is connected to base frame of joint 2. Follower frame of joint 2 is connected to F1 of connecting rod. F2 frame of connecting rod is connected to base frame of joint 3. Follower of joint 3 is connected to base of rigid transform. Follower of rigid transform 1 is connected to follower F1 of piston. Frame R of piston is connected to frame F of joint 4. Then base frame of joint 4 is connected to follower frame of rigid transform 2, and base frame of rigid transform 2 is connected to the world frame. Now, if in a complicated system, if you are not able to connect these systems, I mean, since this is a simple system, so for you connecting them is easy. But for suppose if you are not able to access world frame the way we did it, you can redefine the world frame, and if you just connect this point to this world frame, it will mean the same thing. So just for your note. Now the moment we go to simulation and run our system for 10 seconds, the Mechanics Explorer window will appear. So before we see the motion, what are we expecting? We are expecting this something something like this, correct? The orientations of body 1, 2 and the piston will be like this. And the moment we simulate, we want the motion to be such that, or if you just imagine the motion under gravity, you know that the crank is going to behave like a pendulum. If you just leave this body under gravity, it's like it's going to behave like a pendulum, right? And as a result of which the connecting rod will follow the motion, and then it will trans transform the motion to the piston, where the piston is going to make a reciprocating motion up and down, correct? So let's see. Moment of truth for us. Do we achieve a similar motion? So the Mechanics Explorer window is opened and it's moving, but we can't see because Z is up. So we want the Y to be up. So go to Y to be up. Then you need to press front view. And before anything, I like to press have my visibility of frames to be on and center of mass to be on. And if you go to the beginning of the simulation, so at least this is how I was expecting my system to be. See, exactly the way we defined it to be, and exactly the coordinate systems are also the way we defined the coordinate systems to be. It's exactly following the same thing what we have modeled so far, right? Okay. The moment we simulate, correct. So my crank is following, uh, doing a rotation, like rotating motion under gravity, and the connecting rod is following that motion and transforming that motion to the piston, where the piston is making a to and fro motion, and that's what we expected, right? So things are fine in that perspective. But the moment you go to debug, and you also want to analyze the system. So you go to Simscape and see the statics viewer. We know that the degree of freedom is 1. So let's see, is it? Then go to 3D multibody systems. So over here we define number of bodies, uh, then joints, and so on and so forth. Of course, the mechanism degree of freedom remains 1. Over here it doesn't show -2, even though it's in 3 dimension, and it's such that the degree of freedom should be -2. But if you follow this position constraint equations, of course we are not defining like additional constraints. These number of constraints is 0 because the moment you define additional constraints using additional constraints block in Simscape multibody, then it will show the number to be something other than 0. But since we are defining the joints, so the number of joints are shown here, explicit 3 joints is 3, but the position constraints, so the number of total position constraint is 5, and the number of non-redundant position constraints is 2. So definitely 5 minus 2 is 3. There are 3 redundant constraints, and we never want to have redundant constraints into system. Simscape multibody for this simple mechanism is able to take care of these redundant constraints, but if there is a complex mechanism, I will always suggest you, highly suggest you, that never have redundant constraints into your system. So we need to take care of this redundancy. We need to remove this redundancy because the number of position constraint equation needs to be 2, the same as the non-redundant one. It cannot be 5. So we need to take care of that. How we can take care of that? I'll show you in a while. But before that, then go to Simscape and see the variable viewer. So if you see the variable viewer, you can see different type of joints and if you have defined any priority and their start angle. You see we defined for the first joint the angle to be at 45 degree and the priority to be high. Of course it's starting from 45 degree only, and all the other targets are satisfied as well. So things are fine from the variable viewer as well. Now if you go back, okay, so we need to get rid of the redundant constraints, right? Now, in the beginning, remember I told you like by default we are assuming all these joints to be revolute joints. But then I say, but then I said you that if joint 1 is revolute, joint 3 is revolute, then the motion of joint 2 will follow something similar, right? Just imagine like when and of course you can play around with the other joints as well. You can play around with any of the 3 joints. But over here what I will do, since I have defined a position target in joint 1, so I will not play with that. Then again in joint 2, joint 3, I am using some rigid transform to make the coordinates transform the coordinates, so I'm not going to touch that joint as well. But I'm going to play with joint 2. So I'll remove this revolute joint because of course revolute joint is adding additional constraints into the system. I'll comment it out and I'll use a bearing joint. Now bearing joint is something new to you probably, but if you imagine a bearing joint in practice or in reality, suppose this is the bearing joint, which is the external hub, and then there is an internal ring and ball bearings and things like that. This bearing joint, if this is 3 dimension space and a body is connected with the inner ring and the body is connected with the outer ring, right? This inner and outer ring cannot translate in the x-axis or the y-axis. They cannot. But they can translate on the z-axis. Similarly, this bearing joint can rotate about the z-axis. So there can be a rotation about the z-axis, as well as there can be rotation about the x-axis as well. or the y-axis as well. Why? The moment you connect, like if you imagine a gyroscope, in the gyroscope, things are connected in such a way that it can rotate about the x-axis, it can rotate about the y-axis, it can rotate about the z-axis. So if you imagine a bearing joint in 3 dimension, how many constraint equations it's introducing? Only two. Instead of five in the revolute joint, it's only introducing two constraints. So if you see here already, it allows primitive motion in all the so primitive rotating motion in all the three axes x, y, and z, and primitive translation motion in the z axis, right? So that's how you can see from here. So you can simply connect in such a way that the base frame is still connected to crank and make the connection. So the moment you make the connection and try to simulate your system again, first let's see the animation because I trust my eyes more than I trust these numbers. So if I start from the beginning, I realized instead of the piston in the top, it's now at the bottom, and that's not what we wanted. We want the piston to be here, like shown here, right? So, but if we see the motion remains the same, that it's rotating of the crank is into translational motion of the piston, which is fine. But we want this system to be in the upward direction. So how we can do that? We want we can provide go to this prismatic joint and provide a state target at the position level. So we can define this distance in the position level state target for the prismatic joint. And do we know this distance? Of course, if you know this angle 45, you know the length of body 1, length of body 2, and then you can know the half the length of body 3, then you can, sorry, this point. Then you can clearly define like how much is this distance. But do you really want to do that pen and paper calculation? No. So what we will say, we will make a rough estimate of 1.3 or 1.4, like in the positive direction, right? And say the priority to be low. So it will try to find a solution around this value and save and simulate the system again. Now, when you see the animation now, you realize that the system starts exactly from this point, the way we want it to be, if you see this, and it's also simulating in a similar fashion the way it did with the revolute joint at joint location 2 at the first place, correct? And of course we rename this bearing joint to be, naming is very important, joint 2 crank pin and bearing joint. Okay, and save. I haven't saved my file so far, so saving is very important. So now if I go to the statics viewer window, I will realize now if you'll see the number of total position constraint equation is 2 and the non-redundant one is also 2. So the redundant constraints are taken care of because revolute joint 2 at joint location 2, so the revolute joint at joint location 2 was introducing 5 constraints, and we replaced that with a bearing joint which is introducing only 2 constraints. So the 3 extra constraints are taken care of, and that's what's happening here. And the degree of freedom still remains 1, and this is fine. And I want all of you to always, whatever system you're modeling, never have any redundant constraints. It is very important. Now go to the statics view variable viewer window. Now you will see that of course you have defined now two position target. One position target for joint location 1, which is high priority and starts with 145 degree, which is fine. And then you defined a low position target for this particular joint, and that to the position which you said 1.3. And you see the status is partially fulfilled because the exact value is not 1.3. Exact start value is not 1.3, but it is 1.2913784921692889. Would you able to calculate anything with that accuracy? I doubt. So that's why always define the priority to be low when you don't know the exact value, and it will make things simple. So let's go back to the model, and actually let's go back to the slide. Let's see if everything is uh, defined the way we want it to be. So of course I have taken care of this slide as well. Mhm. Then once our animation is working fine, we also need to plot the results, because plotting is something uh, you cannot show an animation in your report or in any technical documentation, but you can always show the results in form of plots and graphs, right? So let's say I'm interested in knowing the position and velocity of this prismatic joint. So what I can do is I go to this prismatic joint. I say that I want to sense the position and the velocity. The moment I press, you see these ports appear here, the position and the velocity plot, and I close this. So in order to plot this, what I need is I need some kind of a converter, because remember, this is a physical signal. So position and velocity are physical signal, and I need to convert that into a Simulink signal before I can see the Simulink signal. So which converter I will use? I will use this PS Simulink converter. And of course we need a scope in order to view the result. So I select and uncomment. So I just name it as position PS Simulink converter, enter, and then the scope is basically piston piston position, enter, or let's say position piston. The naming, try to define it as simple as possible so that you're able to understand everything from the name. So of course you need a converter, PS Simulink converter, and a scope for the position plot. And similarly we will copy paste this. So select, press Control, and then drag. Also we need one for the velocity port, for the velocity signal. So rename it. Okay. Now simply make the connection. Take the signal coming from port P, connect it to the respective uh, converter, and the signal coming from port V with the respective one here. Perfect. So now if you simulate your system again, let's close these windows. Actually we don't need them at the moment. Okay, so when you simulate your system again, of course the animation will remain the same because we have not done any changes, rather than just adding some new component blocks where we can see the results. So now if you go to the scope for the position of the piston, it will take a while to open. You can see the plot for the position of the prismatic joint, and also the velocity of the prismatic joint. Of course, if you see this plot, you know that the piston is reciprocating uh, to and fro motion use almost with a similar velocity every time. So for the position plot, you can see the to and fro motion, and also for the velocity plot, you can see the velocity is more or less similar in every cycle. Correct? Now let's we also want to log this signal. We also want to save this signal. So how we can save it is we can select the signal coming from the PS Simulink converter, right click and log selected signal. Okay, I think velocity spelling is wrong. Perfect. Uh, okay, now let's go back to the slide. And I hope I'm not blocking anything. Also, you can see the green screen is not working as it should be today. But anyways, so I have covered this slide as well and showed you how to plot the result. Now let's talk something about the kinematic analysis. Okay. Now our basic or our preliminary system, or let's say not the preliminary system, but our slider crank mechanism is ready, where we can actually see the plots as well, right? So now if you simulate the system again after logging, you will see under simulation this data inspector lightens up. And if you go to the data inspector, you can see the position plot and the velocity plot, and you can see different plots here, right? Okay, now we want to carry out a kinematic analysis. And what is kinematic analysis? Kinematic analysis means that the motion that the system undergoes, you are predefining that motion. And in a kinematic analysis, the degree of the freedom is always zero. So the degree of freedom becomes zero no matter what. In our system, we have 1 degree of freedom system, right? So if 1 degree of freedom system is because just one motion is able to define the rest of the system. And if we predefined this motion already, then we are making the degree of freedom to be zero because we are predefining this motion using some additional uh, like constraint or additional input to the system. Correct? So how we can do that? We can do that in a number of ways. But what I will do in this joint one, I want this crank to rotate at anti-clockwise. So for me, anti-clockwise is like this, but for you, anti-clockwise will be like this, correct? Or maybe the other way around, I don't know. For me, my anti-clockwise direction is like this, correct? Anti-clockwise. Okay, so what I will do, I will go to this joint one and I will say that I want to provide an actuation where I am providing the motion. So the motion is provided by input and torque needs to be automatically computed. And the moment I do and close this, you will realize this port appears, this Q port appears in the system. Now what is this Q port? This Q port is basically asking you to define the angular velocity of the system. And this angular velocity needs to be in radian per second is why we are following SI unit, and in SI unit the angles are in radian throughout. So the system solves everything in radian. So we need to provide a a constant angular velocity of 5 radian per second. And how we can do it? We can do that using a ramp function. So if you have followed tutorial 1 already, then I think I defined this ramp function there. Or maybe not. Maybe this is the first time I'm defining. I don't remember. So you go to ramp function. The slope of the ramp function is basically, so ramp function defines velocity versus position plot. and this slope defines the angular velocity in radian per second, and we want the angular velocity to be 5 radian per second in counterclockwise direction, so plus 5, which is fine. Now initial output is basically at what initial angle it needs to start. So for this system, joint 1 initially starts at 45-degree angle, and in radian it will be pi by 4 radian. So that is 45-degree angle, right? And we put the initial output to be here and we press save. So now the moment you try to connect this signal with this, it will not be connected. As I have told you already, incompatible signals in Simscape Multibody will never connect to each other, and that is a good news for us. So what we can do is we can use another converter, which is Simulink PS converter. Why Simulink PS converter is is because the signal coming from the ramp function is a Simulink signal, and this signal Q is actually a physical signal. So we need this Simulink PS converter. So uncomment, and now you will be able to connect it. Now if you go ahead and simulate the system, it will still show an error. It's because we have not fine-tuned this Simulink PS converter. What I mean by that is whenever you are defining an additional constraint into the system, be it at the position level or the velocity level or the acceleration level, you always need the constraints at the other levels as well. For example, if you are defining a constraint in the position level, you need a Jacobian of that at the velocity level and at the acceleration level, right? So you need to have the derivatives of that. So you need to take care of that filtering using this Simulink PS converter. So if you go to this and if you go to input handling, filtering and derivatives. So you are providing only the filter input. You want the derivatives to be calculated. And what order of it will be? It will be always of second order, because in multi-body dynamics we always deal with second order things, because if we are defining things at position level, then we need the velocity and the acceleration level, so second order. And of course we have defined the ramp function to be in radian per second, so we have defined things at the velocity level, but still we need second order filtering for the position and the acceleration level, and then close. So now when we simulate it, what am I expecting? The moment I simulate, I am expecting the crank to rotate counterclockwise at a constant angular velocity of 5 radian per second. And accordingly, the piston will have a to and fro motion, which will be almost with the same velocity, or the reciprocating motion of the piston will be almost sinusoidal. Let's see. Exactly, this is how we imagined our motion to be, right? So the crank is rotating counterclockwise at a constant angular velocity, and the piston is following a to and fro motion. I don't know if it's sinusoidal or not. Let's verify. How we can verify is either we can go to the position plot here. You see it's almost sinusoidal now, correct? And if you see the velocity is also following the same velocity pattern in every cycle. And if you go to the data inspector, you can compare the position plot of this run, which is sinusoidal, with respect to the position plot of the previous run, which is under archive. Wait a minute. Yeah, under archive, this position plot, and let's change the color, change the pattern as well. You see how the system is behaving now. Earlier, also it was maybe sinusoidal or maybe not, but now in the kinematic analysis, it's more perfectly sinusoidal. correct? So you can compare different plots and different data using this data inspector. Perfect. Now let's go back to the slide and so I have covered this slide already, and I told you already that the kinematic analysis degree of freedom is always zero. Now, don't get confused if you go to debug and go to Simscape statics viewer. Uh, Under the statics viewer, if you go to this 3D multibody system, the mechanism degree of freedom it still shows 1 is why I think Simscape Multibody is not taking the ramp component block as an additional constraint, because you see number of constraint is still 0, and that's why it's not taking care of that. But since you know you have defined it, so what you need to do, you need to subtract that one additional constraint from this degree of freedom. So 1 here minus 1 there is 0. Always remember that. Perfect. So I already showed you how the systems will be connected and how the motion will be. So this is fine. Now let's go back. Uh, Now let's move forward to the dynamic analysis. Okay. Now we defined this motion using a predefined motion. So it was a kinematic analysis. Now I don't want this. So I just remove it and comment out. Now I want dynamic analysis, and under dynamic analysis forces are involved. When we were simulating this system under gravity in the beginning, that was also dynamic analysis. Why? Because there was an external gravity force there. Now we want to have this dynamic analysis using a constant torque input to the system. So we want this joint one to not have motion but torque as an actuation. So torque provided by input and motion automatically computed and close. So you see this uh, earlier it was I think Q, right? Yeah, earlier it was something like Q. Now it became T, so torque. And we want the crank to rotate this time clockwise direction. We want the crank to rotate in the clockwise direction with a constant torque of let's say 20 Newton. So how we can define a constant torque? We can use a constant block. So under constant block, I want the value to be minus 20. Why minus 20? Minus is for the clockwise direction and 20 is the 20 Newton per meter is the unit we want, and press OK. Now if you'll just connect, and of course you have taken care of the filtering as well, because you remember whenever you see these two dots in MATLAB 2023 version, or maybe probably in the other versions as well, these two dots means that you have taken care of the filtering with the second order filtering there. So everything should be fine. So now let's simulate the system. So this is my overall system. The moment I simulate the system, before seeing the animation, let's visualize the animation, or let's uh, imagine how it will be. I want the crank to rotate clockwise with a constant angular torque of 20 Newton per meter. So since it's a torque, so what will it will happen? It will provide some kind of an angular acceleration to the system so that the speed, the angular velocity will really increase. It's not constant anymore like in the kinematic analysis part. It's speeding up, right? And as a result of which the piston will follow and the piston will start reciprocating really fast. So with a very high frequency, right? So now let's see the animation. Start from the beginning. So yes, it starts and then we can see that the rotation of the crank is really accelerating and the piston is also really reciprocating really fast, right? And that's what we imagined it to be. And so the animation looks fine to me. If you see the position plot, And if you also see the velocity plot, so this is the position plot of the piston, uh, or of the prismatic joint. You see it's reciprocating, but the frequency, it's increasing, and it's increasing really fast. And at the same time, the velocity is also increasing with high frequency, and that's what we imagine to be. So our animation is following our logic, our plots are following our logic, so we are doing everything correct. If anywhere, if something is wrong, either your logic is incorrect or your modeling or animations are incorrect. They need to be aligned with each other. So if there is something mistake in either of them, uh, think try to think from the basics and then analyze the system, right? Now, if I go to the data inspector, now I want to, let's say, compare the position of this run with respect to the position. Let's not compare position. Let's compare velocity. That will be simple. So this was this purple position. Velocity was that of, uh, I think, uh, this was for the first run, which was under gravity, right? Then this velocity, the green one, is that of when it was following the kinematic analysis. And then this current velocity, which is this one, this is of the dynamic analysis. So of course, the piston is, it's moving really fast, so the velocity is increasing, and that too the frequency is also increasing. You see, frequency is increasing, whereas for the dynamic kinematic analysis, you see it's reciprocating at almost the same velocity, and the frequencies also remains the same. And the same thing you can see for the dynamic analysis under gravity. So the to and fro motion is the same and with almost the same frequency every time. But with constant torque input, you see things are different. So that these are the things that you can analyze. Correct? Now let's go back to the slide. And so I have covered this slide already for you. And I also showed you the position and the velocity of the prismatic joint and also the animation. Now let's move on to the final part. If you realize, we defined everything in such a way that all the joints are ideal. But in reality, is that the case? No. In reality, joints are not ideal and there is some friction between them. So let's say we introduce friction in any one of the joint. Let's suppose I introduce friction in joint 2. Of course, you can do it in the other revolute joints as well. But let's model it in joint 2. Now you can model friction in a number of ways. Usually, if you have the Simscape Multibody Multiphysics library installed in your system, that is an additional package that you need to install along with this Simscape Multibody. You can use this rotational hard stop friction. Using this component block, you can define the friction. So if you go to this block, you can define how is the friction and things like that, like friction in detail, the Coulomb friction, statics friction, viscous friction, and things like that. But I don't want to go here because I think I don't have Simscape Multibody Multiphysics library. So what I will do is there's an alternate method that in the setting of this joint. So if you go to this joint and we want the friction in the rotational axis, and it's rotating about the z axis, right? So in the z revolute primitive, in the internal mechanics, you can see that there's a spring and damping. So under damping, I can define the damping coefficient, and let's say I define 0.015. This way of defining friction is called crude friction, because you are like crudely incorporating into the internal mechanics of the joint like how the friction will be, right? And you press enter and close. Now when you simulate the system, what are you expecting? If I ask you, I am expecting that things, since it's still under constant torque, so things are going to accelerate. I mean, things are going to move at an increasing velocity. But since there is friction, the friction is the friction between these two joints will cause certain dying of the motion. So things will not like really accelerate at that pace, but maybe with an increasing pace, or it will reach to a point that the velocity becomes more or less the same because of this friction, right? So let's animate and see the results. I think I already animated. I animated twice. Wait. Let's start from the beginning. So when I see the animation now, I see that it's accelerating, but now it's not moving at that fast velocity what it was doing earlier, just because of that friction in joint location 2, which is like really good because now the system uh, behaves as it would be in reality, right? And if you see the position and the velocity plot, you will realize that, of course, now it is making a to and fro motion, but the frequency is also increasing, but not that much when there was no friction. And similarly, the velocity is also increasing slightly, but with time, this velocity is becoming more or less constant if you see the amplitude of the velocity. And if you see the frequency is also increasing, but with time it's becoming more or less constant. You see? Correct? And if you really want to compare the results of the velocity, so for example, let's uncheck all the boxes because, yeah, I think we have unchecked all the boxes. Okay, so my this run velocity is something like this, correct? In the previous run, when there was no friction, it was something like this. I'll change the color of this one this time, make it pink. Let's say some other color, correct? And this one was when there was kinematic analysis, and this velocity was under gravity. Let's remove the under gravity one. Okay. So this green one was under kinematic analysis. This was the velocity of the prismatic joint or the piston. Then with constant torque input, this was the velocity where the velocity was increasing, the amplitude of the velocity was increasing with increasing frequency as well, correct? And now this blue plot is the one where you see just introducing the friction in the joint location 2. Of course, the velocity of the amplitude of the velocity of the piston has decreased now, and also the frequency has become more or less constant under this dynamic analysis. So you see, these are the things you can test and try under different situations, and of course you can compare these results here and what they mean. So if I go back to the slide, uh, of course I showed you this slide already by modeling it, and also we compared the result. Then I also showed you this plots and this animation. So I think with that, that's all from my end in for today's tutorial. If you have any questions, please feel free to post it in the comment section of this video. And if you are in class student, please email it to me. I think you guys already have my email address from the lecture material. But for the YouTube audience, please post your questions in the comment section here. And if you email me, probably you will not hear it back from me. But if you'll post it in the comment section, I will try to answer in my earliest possible time. But with that, thank you so much, guys. And if you like this video, please like, share, and subscribe to this channel for more upcoming videos and more interesting videos. With that, thank you so much and have a good day. See you.